Morning AP Physics 1 students. This morning we're going to talk about angular momentum, and we'll talk about how a skater like this can make these amazing spinning jumps and how they can spin around so fast because an object that changes its shape can change their rotation rate. And we'll also talk about how a system of objects that are interacting, if you include all the objects in the system, the angular momentum of the system will remain the same. Angular or rotational momentum has an analog in translational momentum. Now we call this MV momentum. Technically it's translational momentum, for the momentum of an object that is translating along. The description for regular momentum is mass and motion. Remember, left and right make a difference. So for angular momentum, the way it's rotating makes a difference. So this rotation would be different than this rotation. Okay? Or clockwise and counterclockwise. One would be positive and one would be negative. Our equation for momentum is the same as before, mv. And to get the angular momentum equation, all we have to do is plug in the rotational equivalent of mass, which is rotational inertia, and the rotational equivalent of velocity, which is omega. Now there are a couple other ways to find momentum, angular momentum as well. And that is if you have an object that is moving along, you can find its angular momentum by taking its linear momentum, mv, and multiplying by the moment arm, or the perpendicular radius. And we'll talk about that a little later. The units for momentum are kilogram meters per second, and since this is just linear momentum with a radius, then all we do is add another meter. So it's kilogram meter squared per second. Now remember that for linear momentum, if there's an outside impulse, so say Einstein is sitting here and there's a force on him, then his momentum will change. And the same thing will happen in angular momentum. If Einstein is sitting here and then there is a torque over time, then his angular momentum will change. All right? So a torque over time will change the angular momentum. Just like a force over time, an impulse equals a change in linear momentum. Now, if there are no outside forces, if you define the system in momentum so that there's no outside forces, remember that linear momentum or translational momentum stays the same. The same will be true for angular momentum. If you can define a system where there are no outside torques, then the angular momentum of the system will remain the same. So if you include all the interacting objects, then angular momentum and linear momentum should remain the same. So how do we calculate angular momentum? Because we have two different equations. Well, it depends on the object. If we have a spinning shape, like one of these that we saw earlier when we talked about torque, if we have like a hoop or a ring or a basketball or a meter stick and they're spinning about an axis, then all we need to do is pick up their rotational inertia, I, and plug it in the equation to multiply by how fast they're spinning about that axis. Okay, so like for instance, we got a basketball here, mass of m, diameter d, and it's spinning with an omega. What's the angular momentum? Well, let's see, basketball is a hollow sphere, so we pick up this one down here. We plug in our information. Well, mass is little m, radius is d over 2, right here. 2/3 m r squared, or d over 2 squared, times omega, and then finish it out, and we're done. That's the angular momentum of the basketball. Okay, so what if you have an object that's not spinning about its axis, that the axis is off to the side somewhere? Well, as long as the object's not too big, then what we can do is just assume it to be a little lump of mass. Say like in this experiment where we've got a ball spinning around held in by a string and a weight down here. So this mass is small in comparison to its radius. So we can just consider it to be a little lump. And then all we need to do is figure out what's the radius of the circle that it's going around in and multiply by its translational momentum, or m times v. So in this case, it would be mv times the radius of the circle, x. And there you go. One of the weird things about angular momentum is that an object that is moving along in a straight line can still have angular momentum. So this is going to come up later because what we end up with is objects moving in a straight line hitting an object that's going to rotate. And so we have to include them both in a rotational system. And so that's why we will do this. So the way we calculate the rotational or angular momentum of an object moving in a straight line is to just take its linear momentum, m times v, and multiply by the moment arm because the perpendicular radius doesn't change as it's moving along. So like in this example, Mr. Stick has a mass of m, it's running with a velocity of v, and a straight line is shown. What's his angular momentum about this reference point? So all we do is find this perpendicular radius. Remember from torque that this lever arm never changes, right, for this line of action. So it would just be mv times y in this case. All right, so let's try an example. So we have 3 globs of clay that are traveling with a velocity of v towards pendulums as shown in the figure. The clay will hit the pendulum and stick, causing the pendulum to move upward. So say like this one down here, this little mv is going to hit pendulum 1 with a length of 2L, and it's going to swing upward. All right? Now notice that we have an object moving in a straight line that's going to hit this, that's going to rotate about this point. And that's our first question. Where's the rotational point of the system? That includes both the clay and the pendulum. So together, these two will move in a circle about this point. So that's our rotation point, or our axis. Okay, does the clay have rotational momentum before it hits the pendulum? Surprisingly, yes. All we have to do is multiply its linear momentum, mv, times the lever arm, or the perpendicular radius, times 2L. How will we calculate the angular momentum of the clay? Well, we're going to use this one because it's an object moving in a straight line. And then the last question is rank the angular momentums of the clay. All right, so we've answered most of the questions, so let's just go to the next one. And so the top point for each one is the rotational point. Yes, they'll have angular momentum. This is the equation we use. And this one is going to be mv times 2L. This one's going to be 2mv times L. So these two will be the same. And this is going to be mv times L. So this will be half of these other two. So 1 equals 2, and it's greater than 3 for the angular momentum of the clay. Here's another example. We got a tire with mass m and a radius r. It rolls to the right with a velocity of v. Assume the tire is the shape of a ring. So remember that from our rotational inertia table from earlier. Where is the rotational point of the system? Does the tire have angular and translational momentum? Calculate the angular momentum and the translational momentum. So I guess the answer to B is yes and yes. All right, so I'd like for you to figure these out and then go to the next slide, or pause the video and then go to the next slide. All right, so where's the rotational point for the system? Well, this thing is spinning about its center of mass. Yes and yes, there is both angular and translational momentum. And the angular momentum will be I omega because we have an object that's spinning about an axis. This is a hoop or a ring, which was mr squared from our table from earlier. And remember that omega is not given, so omega equals V over R from our video on, rotational kinematics. And then, so we just put that together and we get mRV. And then the translational momentum is really easy. It's just the mass times the velocity. Okay, now that we have an idea of how to calculate the angular momentum, let's see how we can change the angular momentum. Okay, changing the angular momentum requires an angular impulse. Now remember from translational momentum that an impulse changes the momentum of the system. Well, same is true here, except it's an angular impulse changing the angular momentum. So here's an example. We have this solid disk, it has a mass m, it has a radius r, it's spinning with an omega naught. There's some friction here on the axle between this disk and the axle, and it provides a torque. And they want to know what's going to be the rotational velocity final after a period of time. Okay, so the angular impulse, torque times time, will equal the change in momentum. Now remember, this is a rotating shape that has an axle. So that will just be I omega. So I omega final minus I omega initial, that's our change in angular momentum. And our angular impulse will be negative because it's going to be slowing it down due to friction. And so all we do is solve for our final angular velocity. And it's as simple as that. Here's another example where we have some forces that produce an angular impulse and some forces that don't. So here we have a pulley hanging from the ceiling by a thread or a rope, and then there's a thread wrapped around the pulley and a mass right here, and the mass is released and it descends. All right, now looking at this, we have two outside forces to our pulley mass system. We have a tension up and we have a gravity force down. Now this tension up goes right through the pivot point, so it doesn't produce a torque because there's no moment arm. So that one will not do anything to the angular impulse, or sorry, to the angular momentum. Now, on the other hand, down here we have gravity, and the gravity line of action is along this string, and you see how it has a radius, so it's going to make this pulley rotate. So gravity is going to produce a torque. There's our radius, there's our force, R and mg, and then to find the angular impulse, all you do is take the torque and multiply by the time that it's applied, and so it's just going to be R mg times. You can also find the angular impulse from a graph, just like we did before. For an FT graph, you can find the translational impulse. For a torque time graph, you can find the angular impulse. All you have to do is find this area underneath the data. Remember, there could be a positive or a negative area. In this case, there's only a positive area. Everything over here is positive. So just find this area, and for this particular shape, the impulse is 5.3 approximately. So we know how to find momentum, we know how to find impulse. But just like in conservation of momentum for translation, if we have a system that all the objects are included that are interacting, and there are no net outside forces, and that these objects are free to translate, okay? So like they collide with each other, and you include both objects, then you're going to have conservation of momentum. Now the same will be true if you have objects that could be rotating. As long as you include all of the objects that are interacting in the rotational system, and there are no other outside torques, then and the objects have to be free to rotate about an axis or a point, then you'll have conservation of angular momentum. So now I'm going to go through a series of examples so you can kind of see the difference between translational momentum and angular momentum conservation. So in our first one, we have a board here and a dart. And the dart is coming along. The dart has mass and the board has mass. And the dart's going to collide and stick into the board. And this time it's shot at the center of mass. So I have some questions for you. Where is the pivot point or rotational point for this system going to be? Now, this is a board that's on a frictionless surface of science, and we're looking at it from the top. So it's free to move, all right? And what will happen when the dart hits the board? Okay, well, so this dart's going to hit right at the center of mass. And remember, the center of mass is the natural rotation point for a system. So it's going to hit right at the center of mass. So when it does, it will not produce a torque because there's no lever arm between the line of action and the pivot point. So it won't rotate when it hits it. However, we have two objects that are interacting, so the object should translate forward afterwards. So it should look something like this. Translational momentum, when the dart hits, should be conserved. So the board will speed up and the dart will slow down to a common velocity at the end. mv of the dart before equals m plus mv of the dartboard system afterwards. But it's not going to rotate because there was no lever arm or torque produced outside of the pivot point. Another way to look at it is that since this is the pivot point, there is no angular momentum to start for the dart because its line of action passes through the rotational point. All right, so now what if we shoot the dart down below, down here, at a distance r perpendicular? So now there's a lever arm. What's the board and dart going to do now when it hits? Well, this time the board will rotate as well as translate. Now the interesting thing is nothing in the translational momentum has changed. We have an mv for the dart before, we have an m mass of the board, and the dart
combined afterwards. So this final velocity will be exactly the same in this case or in this case, exactly the same. But what we add this time is we add a rotation at the end because this dart has an initial angular momentum about the pivot point because there is a momentum with a radius. So the final omega of the system is determined by the original momentum of the dart. Both momentums are conserved. Okay, here's our third example. This time I have a board that's hanging downward, like, say, like this pen. I'm holding it down. And it's pivoted at the top, okay? And this time the dart's going to come along and hit again at the center of mass. So where's the rotational axis this time? Well, it's going to be up here because it's forced to be at the top, okay? And how is the system going to act afterwards? All right, well, this time the board can only rotate about this point. So this point is providing an outside force on the system that will not allow linear or translational momentum to be conserved. So it's not conserved because it can't translate along. It can only rotate about this point. So translational momentum is not conserved in this case. However, there is a point, an axis, about which the thing is free to rotate. So this thing will have conservation of angular momentum about this point because there's no outside torques here. So the original angular momentum between this dart and this pivot point will equal the final angular momentum of the system about this same hinged point afterwards. Okay? So if the dart hits up here at the hinge, then it won't rotate and it won't translate. The farther down the dart goes down the board, down at the end, the more it's going to rotate. Okay? So the greater radius we have here, the more angular momentum we start with because we have the same MV for the dart, but a bigger perpendicular radius. So that will mean a bigger rotational speed for the board afterwards. This time the board is hinged at the top and hangs straight down due to gravity. A ball travels and collides with the board. How would you change the velocity of the ball to increase the height that the board swings to? Okay, think about that. How would you change the mass of the ball to increase the height that the board swings to? Because we want this board to go out farther. What kind of collision would we have that would make the board swing as high as possible? Should you pick elastic or inelastic? And then, is it possible for the ball to hit the board, and the board not swing at all? Sorry, my English is bad. I typed this late last night. All right, see if you can answer these questions and then pause the video. All right, here are our answers. So if we want this board to swing as high as possible, we need to start with the maximum amount of angular momentum. And we can do that by increasing the velocity. All right, easy. We can also do that in question B by increasing the mass of the ball. So if the mass is bigger, it will make the board swing up higher. Or we could increase the radius from the pivot point. So any of these three will increase the angular momentum initial, which will increase the angular momentum final, which means the board will swing higher. Okay, what about the type of collision? Well, if it's a inelastic, or let's take the extreme, perfectly inelastic collision where it hits and sticks to the board, well, then this ball will have the small change in momentum. It's only going to slow down a little. So it's only going to transfer a little momentum to the board. So we want this ball here to transfer as much momentum to the board as possible. Remember, the change in momentum of the ball equals the change in momentum of the board. So the momentum lost by the ball has to be gained by the board. So if the ball hits and bounces backwards, it will have a much larger change in momentum. So therefore, it will give more momentum to the board and the board will go higher. So we would like an elastic collision. All right, is it possible to hit the board and it not swing at all? And the answer is, sorry, my English is all screwed up in this sentence. The answer is yes. If you just aim for the hinge, then we'll have no radius, no perpendicular radius. And so there'll be no initial angular momentum, so it won't go anywhere. All right, let's look at an example. We have a child that's running and jumps on a merry-go-round as shown in the figure right here at the edge. After the child lands, the merry-go-round will rotate. So the child's going to run, stick to the merry-go-round, and rotate around. Okay, which way will the merry-go-round rotate? Well, that's pretty easy. It's going to rotate, as we see it, counterclockwise. Is the child's final velocity faster or slower than initially? Well, when the child runs and jumps on, the child's going to slow down as the child speeds up the merry-go-round, right? And then calculate the final rotational velocity of the system. So here we go. We've already got that it's going to go counterclockwise. We know the child is going to slow down. Now, we could argue this from a couple of ways. We could say that momentum from the child is transferred to the merry-go-round, so therefore the child's going to go slower. Or we could say that there's frictional forces between the two. Friction between the child and the merry-go-round speeds the merry-go-round up. Friction from the merry-go-round, Newton's third law, back on the child will slow the child down. And then here's our conservation of momentum. First, I want you to note that linear momentum is not conserved because this axle will keep this disk from moving, translating. But it is free to rotate about this point. So about this point, we have the child has a perpendicular radius, or moment arm, times mv. And then afterwards, the child will be on here, same radius, mv, but this will be the final velocity. And then the I omega for our rotating shape about an axle. Now remember that this omega here at the end and this velocity here, these two must be related because remember omega equals v divided by r from kinematics, or v equals omega r. Another thing I want to note about this problem is that it's an inelastic collision. So therefore kinetic energy will not be conserved, that we will lose kinetic energy in this type of collision because they hit and stick together. Here's another example that's actually quite similar. This time we're going to drop a lump of clay on a rotating disc. The clay is going to hit and stick to the disc. It's a radius of r from the axle, and then we have data about the rotating disc itself. What happens to the rotational velocity of the disc? Explain, and set up conservation of angular momentum equation. So first of all, the disk is going to slow down due to conservation of momentum. This disk is going to pick up mass, so the rotational inertia of the system is going to increase, therefore the rotational velocity of the system must decrease. You could also say again by friction, friction speeds the clay up, thereby slowing the disk down, Newton's third law. Now, conservation of angular momentum, before and after about this axle should be the same, so it's free to rotate. So I have an I omega naught for my original rotating disk. Then I have an I omega final for the final omega of the disk. And then I have just a lump of mass that's going to be going around a point. So that's going to be an RMV final. Now remember, this is a rotating disk, and from our rotational inertias from earlier, we know a disk is 1/2 mr squared. And we also know that velocity equals omega r, so I can make this substitution in right here. I'm going to make this substitution in here and here. And when I do that, I'll end up with this big, ugly equation that we could cancel some things out if we wish. But if you have to do this on the test, you can just leave it right there if you'd like. This is another inelastic collision. Therefore, the energy of the system will decrease. We have gravitational potential energy to start, and we have kinetic energy, rotational kinetic energy of the spinning disk. When the clay hits this spinning disk, it's an inelastic collision, and so therefore the final rotational kinetic energy of the system must be less. Where should we drop the clay to slow the disk down the most? Well, why don't we put it way out at the edge? Because look, here is our, well, let's go here. Here's our equation. If we increase the radius of where the clay drops, then this number will be bigger and therefore decrease the final omega of the disk. Sometimes you can have an outside force on an object but this force does not produce a torque. Here's an example. We have a ball on the end of a string. The ball is going around in a circle, and we're going to pull the string in so the ball will take a path that spirals inward. Now, this tension is an outside force on the ball, no doubt, but it goes through the pivot point. Therefore, it doesn't produce any net torque. Since there's no net torque, the angular momentum of the system must remain the same. So, as the radius goes from large to small, and the mass of the ball remains the same, then the velocity of the ball must increase. So as it goes around and around and around, it goes faster and faster and faster. Now, the kinetic energy increases because the tension is an outside force. It's a non-conservative force. And it's doing work as it pulls the ball inward, so it's increasing the kinetic energy of the system. Here's another example where the force will go through the rotational center. We have a planet and a star, and the gravity on the planet from the star passes right through the pivot point or the rotational center of the planet at that instant. And so therefore, it doesn't produce any torque, which means it won't change the angular momentum of the system. So as the planet goes from apogee, the farthest point in an elliptical orbit, to perigee, the closest point in the elliptical orbit, the radius is decreasing, and therefore the velocity must increase. Now, since gravity is a conservative force, we're going to have conservation of energy for our planet-star system. So as the planet speeds up, as it gets closer, its potential energy is decreasing because it's getting closer, but its kinetic energy is increasing. At apogee, its potential energy is getting larger because it's getting farther and farther away from the star as its kinetic energy is decreasing, and these two must be the same. We see this in things like comets out in space. So there's thousands and thousands of comets that go around the sun, but we rarely see them. One, because sometimes they're really small, but other times because they don't spend much time around the sun. They're in highly elliptical orbits. They spend tons of time out here because they're going really slow around this part of the orbit, and then they rocket past the star in only a couple of months. Now, here's our last topic, the fact that an object itself can change its shape internally. And when you change the shape, you change the rotational inertia. And when you change the rotational inertia, you can change the rotational speed. So here's an ice skater at the end of her routine, and her arms out, and her legs are out, so she has a large rotational inertia and a slow omega. But as she pulls her arms inward and her leg inward, then her rotational inertia decreases. And since there's no outside torques, her angular momentum must remain the same. So therefore, her spin rate goes way up, and we see this all the time in ice skaters. We also see this in divers. The diver goes up, they're spinning fast as they tuck inward, and then right before they hit the water, they seem to stop spinning. Really, they don't stop spinning. They just slow their rate of rotation down so they can enter the water vertically. If they would do this too soon, they would continue to rotate, but just at a slower rate. So this goes back to our original slide. So how do they perform these really amazing jumps and with so many rotations so quickly? Well, what they do is here we go, an example. So they're rotating, and if they want to rotate faster when they're in the air, they pull their arms and legs inward, which means they spin faster because their angular momentum stays the same. So here you can see her in the picture here, tucking her arms in and her legs in as she rotates, and then they're wide out again as she wants to slow down and land. And then when she jumps again, she tucks in to spin fast again, and then her arms and legs go out. That's not just for balance, that's actually to help them slow down so that when they hit the ice, they're not going too fast and they can land the jump. So another one is in gymnastics, the vault. So a gymnast will come and vault, and if they want to tumble really fast, then what they'll do is they'll tuck their arms and legs in, make themselves more like a ball so they have less of a radius. they lower their rotational inertia, and then they can go head over heels much faster. If they want to instead rotate along the long axis, kind of like a pencil rotating this way, then they pull just like an ice skater. They pull their arms and legs in to rotate like a pencil and then land. And right before they land, they always put their arms and legs out so that they slow their rotation rate down. This can also be true for a system of interacting objects. So the system itself can change because parts of the system are moving around. But if there's no outside torque, then the rotational angular momentum of the system will remain the same. So here we have a child on a rotating disc like a merry-go-round, and we're looking at it from the top. This child can run one way or another way or outward or inward, and they will change the rotational rate of the merry-go-round. However, they will not change the angular momentum of the system. So like if the child goes out, they're increasing I, the rotational inertia. So the system slows down, but the angular momentum stays the same. If they go inward towards the center, then they will decrease the rotational inertia, and the omega will spin up faster, but the angular momentum remains the same the entire time. So the child can't do anything to change the angular momentum, but they can change the rotational velocity. And that's it. So there's angular momentum. I know this was a long video, and there was a lot in it. Thank you for hanging in there, and our next one up will be energy. Bye-bye.